Welcome back. In this section, we're going to introduce one of the two derivative tests, the first derivative test, which is used to figure out the location of relative extrema. Before we do that, though, let's just sort of have a flashback to our pre-calculus days talking about increasing and decreasing. So we've got a function, some sort of function defined over an interval, and if we pick any two x values in that interval, and x1 here, that's the smaller x value, x2, that's the larger x value, if the smaller x value always has the smaller y value, in other words, if we're looking at our graph going from left to right, if the y values go from smaller to larger, then that means our function must be increasing. If the reverse happens, as we read our graph from left to right, from smaller to larger x value, if the y values go from larger to smaller, then our function is decreasing. We're heading downward. And of course, if the y values are the same, if they're always the same y value as we read our graph from left to right, then we would have something where it's a constant function over that interval. So looking at these, it's pretty easy to just by sight pick out where we're increasing and where are we decreasing and where are we constant. So just sort of reading from left to right, I can see that starting at -2, going all the way up to 0, my graph is increasing. So we're increasing on the interval from -2 to 0. Then from 0 to 1, over that interval of x values, we're constant. Then from 1 down to 3, we're decreasing. And then for x values from 3 to 4, we're increasing. We are continuing to increase, going up as we go from 4 to 6. And then we're constant between 6 and 8. One little thing I wanted to mention about this, actually two things. One is, you'll notice I had to split up my intervals separately, 3 to 4 followed by 4 to 6. And that's because at 4 itself, we're not increasing, we're also not decreasing. That's because there's no function happening when x is 4. So if you had said we're increasing from 3 to 6, that would actually be incorrect. Because you're not increasing at 4 because there is no graph at 4. Because there is no graph at 4, I really have to split it up into two separate intervals. The other thing I wanted to just sort of put out there for just a brief moment, and we're going to circle back to this, you might notice we have two intervals that are side by side that are increasing, but the shapes are not exactly the same. So if you're thinking about how we're increasing from 3 to 4, that's not exactly the same shape as we're increasing from 4 to 6. The shape looks a little bit different. And we're going to talk about that. They're different in their concavity. That'll be the topic for the following section. Okay, so now we have arrived at an important theorem. This is our test for increasing and decreasing functions, which probably should not be a big surprise will involve our derivative. Remember that our derivative gives us the slope of the tangent line at that point, and of course, the slope of the tangent line is also the slope of the function at that point, how that function is increasing or decreasing. We know positive slopes mean things are increasing, negative slopes mean things are decreasing. So, if you had a function that's continuous and differentiable, then if that function's derivative is always positive in an interval, then f must be increasing on that interval. And if the derivative is always negative on that interval, then f should be decreasing on that interval. And if our derivative is always 0, then f should always be a constant. Just sort of circling back to the last example that we had, we can sort of take a look at that and see that in action, that what's going on here is we're going from -2 to 0 in the x direction. The slope for this little chunk of the graph is a positive slope, and in fact we are increasing in that interval, as opposed to something like from 1 to 3 where we're heading downward. Any tangent line you draw on that interval is going to be something that has a tangent line with a negative slope. We're decreasing over that interval. So that's kind of the idea here, is that if we're looking for where are the increasing or decreasing intervals, think about the picture we had just finished with and notice that where things change from increasing to decreasing or vice versa would be at places where either there's maybe some sort of discontinuity where we had a break or a jump or an asymptote, or perhaps places where the function changes direction. That might be something where we change from increasing to decreasing or change from decreasing to increasing. Or perhaps it might be a place where we've got a sharp corner, like in the absolute value function. That's also a place where you change from decreasing to increasing. Now, if you're thinking about what these things all have in common, if you have a discontinuity, if you are having any sort of a break, well, then the derivative does not exist. And same thing is true if there's a sharp corner. Remember, we said back in the differentiability section that having a sharp corner would be one reason why you might not have the derivative. So if you're looking at places where the derivative does not exist, that's going to tell you that's a potential place where you might be changing direction, or where the derivative is 0. That also might be a place where you might be changing direction. And of course, all of those, where places where the derivative is 0 or places where the derivative doesn't exist, those are our critical numbers. So really what we're saying here is that our function f can change direction from increasing to decreasing only at critical numbers. So that kind of gives us a hint as to how we're going to find our increasing and decreasing intervals. First, if we've got a function, if it's continuous on some open interval, then we just need to go ahead and find all of our critical numbers. So all the places where the derivative is either 0 or undefined, and then put all those critical numbers on a number line, and that'll split our number line up into smaller little intervals. And then inside of each interval, we're going to pick a test value and find out what's going on with our derivative. Is our derivative positive or negative in that interval? And then using the previous theorem, we'll be able to say, well, since in that interval my derivative is positive, therefore my function must be increasing. Or since my derivative in the interval is negative, then my function must be decreasing. And that's how we'll tackle these sorts of increasing and decreasing interval problems. So let's start with this one. We want all the open intervals where this function is increasing or decreasing. So first thing I'm going to do is find all my critical numbers. And I know for finding critical numbers, I'm going to first find my derivative. So when I do that, power rule says 6 times 3, power would come down to give me 18, and power would get reduced by 1. For 9x squared, the power comes down. 9 times 2 is also 18, and power gets reduced by 1. I know that definitely there are no places where the derivative does not exist. So definitely my derivative is defined everywhere, so I don't have to worry about those kind of critical numbers. I have to worry about where is my derivative, though, equal to 0. That will be my critical or those will be my critical numbers. And for that, it's pretty easy for me to solve for x. I can see that I've got 2 values for x. One of them is that x is 0, and the other one is that x is 1. So our domain for our function is all the real numbers, and we found that there's only 2 critical numbers which is one of them at 0 and one of them at 1. So that's what I mean by splitting our domain up into little intervals. I've got all the numbers less than 0, all the numbers between 0 and 1, and all the numbers that are larger than 1. So what we need to do now is select x values, 1 in each of those intervals, and then find out what does that do for our derivative. What is our derivative doing in each of those little regions? So for example, for things that are less than 0, a nice convenient number that's less than 0 might be -1. And I'll find out what's going on with my derivative at -1. I know it's either going to be positive or negative. It's not going to be 0 because we already found where is the derivative 0. So in this interval, the derivative is either going to be only positive numbers or only negative numbers. And so now let's find out which it is. So putting in -1, I wind up getting positive 36. So that means my derivative is increasing. Or sorry, my derivative is positive, which means my function is increasing. Okay, and I'll do the same thing in the other intervals. Between 0 and 1, I'll pick, let's say, 1/2. And when I put 1/2 into my derivative, I get a y value of 9/2 negative. So that tells me my derivative is negative, which means that f is decreasing. And then for values larger than 1, I'll go for 2. And I find that f prime at 2 happens to also be positive 36. So in that interval, f prime is positive, which means that f is increasing. Okay, so now we're ready to summarize the intervals where we're increasing and where we're decreasing. Here I'll say, where are we increasing? We're increasing from the far left all the way up to 0, that first interval. That was our increasing interval. And we're also increasing from 1 and onwards to the right. And then as far as where are we decreasing, we're only decreasing in one interval, and it's that little interval from 0 to 1. All right, so we've figured out where our function f of x is increasing and where is it decreasing. Let's do another example. So I've got a rational function. I know definitely that this is not defined at x equals -2, so I know already -2 is going to show up on my number line because that's going to be one of the places where my function splits up. And let's see where else we can find what other places that I might have my function g of x changing direction. And those will be at the other critical numbers, the other places where g prime is equal to 0. So let's go on. Finding our derivative, the bottom is going to get squared. And then the bottom comes up as it is. And the derivative of the top, the derivative of 3x plus 2 is just 3, minus the top as it is, and then times the derivative of the bottom. And so for the bottom, we're going to do a little chain rule moment. The power comes down. The power gets reduced by 1. And then the derivative of the inside, the derivative of x plus 2 is just 1. Okay, and just to clean this up, I can see that I have x plus 2's that I can factor out of both terms, and a 3 that I can factor out of both terms. And in fact, as far as the x plus 2's go, I've got 3 here and 2 there. I can factor 2 out of both terms. So that means in the first term, there's only going to be a single x plus 2 left behind. And in the second term, I'll have that 3x plus 2 left behind. The 3 factored out and the x plus 2 squared factored out, so that is that. On the denominator side of things, I'll have x plus 2 cubed and then squared, which is really x plus 2 to the 6. I'm going to do a little bit of cleaning up here. One thing that I can do to clean up is the x plus 2 squared from the top can cancel with 2 of them from the bottom. So that for g prime, I'm now going to have that x plus 2 to the 4 in the denominator. And in the numerator, if I were to clean up what's inside of my little bracket that I've got here, I'd have x plus 2 minus 3x minus 2. That would all clean up to give me just negative 2x. So in the numerator, I'd have 3 times negative 2x, which is negative 6x. And now I can say a couple of things about this. One of them is that as far as critical numbers goes, we're going to get one of them that's going to show up for us for where g prime is equal to 0. And that's because if you're looking at a rational function and wondering where is it equal to 0, that would be where just the numerator is equal to 0. So 0 is a critical number. Also, we notice the derivative is undefined at x being negative 2, but we already noticed that, so we already really knew that negative 2 was going to wind up being a critical number. So nothing really surprising or shocking there, so that means we're ready to go ahead and find out what's going on with our function. We have our critical numbers, the one of them at negative 2 and one of them at 0. And now I'm going to pick my values for x. I'm going to go with, for number less than negative 2, we'll go with negative 3. And between negative 2 and 0, I'll go with negative 1. And bigger than 0, I'll go with 1. So when I look at g prime of 1, putting in 1 for my x value in my derivative, I'll have negative 6 on the top and then 81 on the bottom. Negative 6 over 81, or same thing as negative 2/27. So therefore, our derivative is negative. In that interval, we must be decreasing. And for negative 1, g prime of negative 1, when I put that into my function, I get just positive 6 over 1 to the 4, or positive 6. So in that interval, I am increasing. And then when x is negative 3, g prime of negative 3, that'll give me 18 in the numerator and 1 in the denominator, so just 18. So it looks like we are increasing there again. So where am I increasing? Where am I decreasing? I'll say again, for increasing, we have 2 intervals. We have everything up to negative 2. We're increasing, and we're also increasing between negative 2 and 0. I do want to caution us, because you might be tempted to look at that and just say, oh, we're increasing all the way up to 0. But of course, that's not the case. And the reason it's not the case is because we know that there's a vertical asymptote happening when x is equal to negative 2. So actually, there is no graph when x is negative 2. So if you said you were increasing all the way across up to 0, that would include the negative 2, which we cannot include. So I do have to split my increasing into 2 separate intervals. For decreasing, I have only one interval where I'm decreasing, and that is that last interval for the numbers that are larger than 0. Okay, one last one. We've got sine and times cosine as our function. Nicely enough, it's given to us on the domain from 0 to 2 pi. So we don't have to worry about all the possible infinitely many critical numbers we might have, just the ones in that little interval. First things first, we know sine is nice and continuous everywhere. Same thing with cosine. Sine times cosine, it's two continuous functions. It'll be continuous everywhere. We know there's not going to be any discontinuities with this function. So let's get into finding some derivatives for this then. So I'm looking at this and I notice it's a product, so I guess I'm going to need product rule. First thing as it is, derivative of the second. Derivative of cosine is negative sine. And then plus the second thing as it is times derivative of the first. And derivative of sine is cosine. So I can see that I'm going to have a negative sine squared and I'm going to have a positive cosine squared. So I'll say I've got cosine squared minus sine squared. If we're looking for critical numbers, I can see f prime, there's no places where this is not defined. So the critical numbers would just be where f prime is equal to 0. So we would need to solve where is cosine squared minus sine squared equal to 0. For this one, if I were to solve it, I could say to myself, well, I could move the sine squared to the other side. I'd have cosine squared equals sine squared, and then I could divide both sides by cosine squared. And the reason I would do that is because sine divided by cosine is tangent. So really this would give me that 1 is tangent squared, or that tangent is plus or minus the root of 1, or in other words, plus or minus 1. And we know for tangent where it gets those 1 and negative 1 values. It gets them at pi over 4, and at 3 pi over 4, and 5 pi over 4, and 7 pi over 4. Those are the different places where tangent is equal to 1 or negative 1. The one thing we should probably concern ourselves with was just at that stage, though, where I did that division. Remember, when you divide by something containing a variable, potentially you might be losing solutions. So we have to ask ourselves, when cosine is equal to 0, is that a thing that might be a solution? And good for us, we know cosine is equal to 0 at pi over 2 and at 3 pi over 2, except at those places sine is equal to 1 or negative 1. So left side and right side of our equation wouldn't be equal to each other. We don't have to worry that when we divided by cosine, that when cosine is 0, that might have been a solution. It definitely is not. So we didn't lose any solutions. Good for us. We found 4 solutions, all those odd pi over 4s. And so now I guess let's get ourselves ready to start testing things. So I'm going to put in all of my numbers, and because I'm looking at a domain that's not all the real numbers, just from 0 to 2, then when I look at my little interval, it'll be starting at 0, going all the way up to 2 pi, and I'll put my other numbers along that interval in order from smaller to larger. So I'll have pi over 4, and 3 pi over 4, and 5 pi over 4, and 7 pi over 4. For some of these, it's easy enough to check them. So the values that I'm going to choose between pi over 4 and 3 pi over 4, I'll choose pi over 2. And between 3 and 5 pi over 4, I'll choose pi. And between 5 pi over 4 and 7 pi over 4, I'll choose 3 pi over 2. So those will be nice, convenient numbers. And whenever you're doing this, you're always going to want to choose something that's convenient, not inconvenient. So all those multiples of pi over 2, those are nice, good choices. I can't use 0 and 2 pi, unfortunately, because those are the ends of my interval. So I need something between 0 and 4 pi, and between 7 pi over 4 and 2 pi. So between 0 and pi over 4, I'll go for pi over 6, so 30 degrees. And then I'll use 11 pi over 6, 330 degrees for that last interval. And now when I put things into f prime, and find out what I get. And I should really say instead of x, there should really be theta, because that was my variable. So I'll change that so I'm doing things properly. There we go. So when I put these into f prime, I'm going to only care about, do I get something positive? Do I get something negative? So I'll start with the easy ones. And so for f prime of pi over 2, if I put that in, cosine of pi over 2 is 0, sine of pi over 2 is 1, 0 square minus 1 square is negative 1. So derivative is negative. We are decreasing. At pi, cosine is negative 1, sine is 0. Negative 1 squared minus 0 squared is 1. So f prime of pi is 1. That's positive. We are increasing. And at 3 pi over 2, cosine is 0, sine is negative 1. 0 minus negative 1 squared is 0 minus 1, or negative 1. So f prime of 3 pi over 2, that's negative 1. So we are decreasing in that interval. Okay, so the only one that I'll have to do any real calculating with is the pi over 6 and the 11 pi over 6. F of prime of pi over 6, that's cosine squared of pi over 6. Cosine of pi over 6 is root 3 over 2. So cosine squared would be that squared. Sine of pi over 6 is a half. And when I clean that up, that would give me 3/4 minus 1/4, which is 2/4, or a half. So positive value for f prime, we are increasing. And then I'll do the same thing for 11 pi over 6. F prime of 11 pi over 6. At 330 degrees, cosine is positive root 3 over 2. And sine is negative 1/2. But that still gives us the same 3/4 minus 1/4, which is a half. So our derivative is positive. We are increasing. And now I can make my little note to myself. If I wanted to write it over here on the side, I could say, where are we increasing? There's 3 different intervals. We've got from 0 to pi over 4. We have from 3 pi over 4 to 5 pi over 4. And then we also have from 7 pi over 4 to 2 pi. And then as far as where are we decreasing, there were 2 intervals for decreasing. One of them was pi over 4 to 3 pi over 4, and then the other one was from 5 pi over 4 to 7 pi over 4.